record this one. Okay, then I'm gonna share the other screen. Okay, let me see that. See, go to week 2. To lecture this one, practice discussion week 2. Assignment, go to assignment. Assignment on my side, I have to do like that. Oh, these people, when they set this up, it's not been attached to this one, no?
Right, I didn't see anywhere.
Oh, yeah, because I saw that earlier, it's been attached to this one. That's why I thought, hold on, let me see. Hey, Angela, good evening. We just started, okay? We were looking for that test 2, the homework 2, and then see whether that data being attached to this one, but
it's under content and student resources. Shared
oh, but they are supposed to put it over here too, but seems like yeah, but they don't guide very clearly over here, because of the problem, these all the questions and all the homework, everything set up by the university, and then we cannot do any changes. All that set up. Because of that, I can go over here and do the edit and do some kind of adjustment. But other than that, I can attach to this. And I want to make sure that midterm test and all other homework, the data going to be attached over here. So let me see that one. Where that? Yeah, it's not. Click on the week 2 assignment, but they don't even say clearly, because I was looking. What happened to this? Why I cannot? Yeah, there you go. Let me see. Okay, they go to content, student resources. Yeah, see, it's homework 2. Yeah, it's on the shared document then. This one. Let me see that I should have that one somewhere. Okay. This one, October, data for the homework 2. Homework 2 BG all dot SAS. This data set, no. Is it the same data set? Some okay. To okay. Assignment, go to assignment. Yeah, this is what you're gonna see as a student. So I'm gonna get out of this one and to now it's there. Okay. So I pretty much can do for all the assignments as well as for the midterm and the final exam, the same thing, that it's easy for you guys to just open from here. And then Where is that one? Is the one that I just attached. I don't see that. Let me see what happened. B2 assignments. Go to assignments. Edit. I know what happened. Okay, it's not being saved. Just save. Save. Okay, so see. Yeah, now it's easy. Okay, pretty much for all other assignments, I'm going to attach that one as well. Okay. Okay, let's go ahead and look at that our discussion what we had for that chapter 4, mainly that chapter 4. We can remember that we were related to those PowerPoints. We were working on this one, and while we were working on this one, when we were done with this one, we halfway through, we did up to here, and these ones we didn't do. But if you go ahead and then to complete that discussion, that chapter 4, we have this model, you know the model. This one, this one you can say k many variables. In our example, we have a 2, k equals 2, like that. Okay. So chapter 3, then we talk about this one. When we talk about this one, this one. So how do you interpret? See? So after that, we get this, especially that when you're gonna run this one on with the SAS, and then when you get the coefficients. See, coefficients. See, these are beta naught, B naught, B1, B2. How do you interpret that one? See, and then on the other hand, that recall that the sales is in thousands and the advertising and bonus are in hundreds. So it means like whenever we have value, it should be multiplied by, sales should be multiplied by 1,000, and these numbers should be multiplied by, if advertising is held fixed, see, advertising is held fixed, sales increase, 1,864, each $100 bonus paid. See? Each $100 bonus paid. See, bonus has been given in, see, every $100 bonus, every unit, I'm gonna say 1 unit. This is just like a what? This is the slope. This is like the marginal. Marginal by fixing this one, this is the marginal that sales with respect to bonus. See? If you increase that bonus by 1 unit means like 100. $1 has been multiplied by hundreds because this is been given by hundreds. Per that increase of that one, how much the sales gonna increase? Sales gonna increase by 1860. It is like an increment. That's like the slope. That means this slope, this plane. You see, if you fix this one, how that will be inclined with that this line. You can get the line to this side and see how this line been inclined with this axis. That's the inclination. That inclination, no, you can say the marginal. But you cannot talk about the two marginal at the same time. One marginal, one has to be fixed. You have to be fixed this one. This has to be fixed. On the other hand, in order to get the other one, you have to fix this one. If bonus were fixed, sales increased the 2,470 because this has to be multiplied by 1,000. This number for each $100 means 1 unit spent on ads. See? They were increasing. Positive means increasing. See? That's the physical interpretation for those two, beta 1 and beta 2. in the context of given problem. And this is what, when the no money, when even a penny has been spent on advertising bonus, your sales gonna go negative. See, negative sales. See, if there are negative sales, means like if there's a like a that if you are losing money, or if you want to make that one sense, that sometimes you're gonna subtract that mean value from this advertising and then bonus mean values from there one, and then readjust this formula. Okay, we don't talk about that one here, but make sure that when you're gonna just explain that those being beta 1 and beta naught especially, and this one becomes like a, this one means like a, this is the intercept. Intercept means like a, when this guy and this guy is 0, what would be the value of sales? It's gonna be negative 516,000. So pretty much similar fashion. This one not like that. These are slopes. The slope, or this is the inclination of y, or that the plane with respect to the advertising axis. This is the inclination too of the sales, or that regression plane with respect to this axis bonus. So that increment is by how much it's been increased or decreased. Okay, if it's negative, you have a decrease. See, then we did some inferences. See? Okay, we talk about that one assumption. So make sure this is a very this is a something that we have to take into account at this stage. What this means, we're going to talk about the assumptions. There are 4 assumptions. 4 assumptions, what that means? 4 assumptions means the assumptions for that model to work. What model? The model that we were talking about, the model, see, multiple linear regression. We can give that model by this way: beta naught plus beta 1 x1 plus beta 2 x2, okay, plus beta k xk. But in our example, for time being, I'm gonna working on 2 beta naught equals beta 1 x1. X1 means advertising plus beta 2 bonus. Later on, we can add even the market share and then competition. Okay, plus epsilon. I'm put something called epsilon. This one is epsilon. Epsilon for error. That's the error. Plus epsilon. This is the model. There's an error being incurred within this model. If there's no error, this part is called the noise. See, perturbation. It's been perturbed by this guy. This guy is the one that played a heavy role in statistics, data analytics. Because of this guy, we have to use the statistics. Otherwise, this part is very deterministic. Up to here, deterministic. This guy is random. Random means probabilistic. Yes, the whole thing becomes random. It's a random values. See, random, probabilistic. So error is playing a heavy role. Error is playing a heavy role. That's why in a model like that, okay, this is for the population. Okay, this is for the population. We know this for the population. In the population, instead of when you put the y, but if you, that's a y, but this is the model. It's the model. But when it's come to the equation of the plane, equation of the regression plane, you're gonna write like this way: expected value of y given x, okay, given x equals beta naught plus beta 1x, beta 1 advertising plus beta 2 bonus. See, you don't have error term. That's the equation of the regression plane. See? The expected value of y here means, you cannot say that it's a y here means sales. Yes, yes. For given x1 and x2, actually that given x1 and x2. Okay, you can say given x1 and x2. Both. We don't have one only, we have a two. For a given x1 and x2, what would be the value of y? So for a given x1 means given value of advertising and bonus, what is the value of this one being given as a like a expectation? Expected value of given y given x1 and x2. X1 and x2. See? X1 and x2. X1 comma x2 is nothing but expected value of sales given advertising and bonus. Yeah, expected value. See, expected value, average for everything, expected value. That's the equation. See, I dropped that epsilon. I drop epsilon. If you write y, you write like this way. You saw that one very clearly here. You saw that one very clearly here. The population version, when you have, okay, can you remember we were talking about, see, for given x, see, you have this kind of planes. Okay, this is x1, this is x2. But I don't want to draw the three-dimensional picture, but it's going to be three-dimensional. Why would be sales? This should be two-dimensional, this one. This one two-dimensional. Something like this. See? Something like that on one x1 and x2. X2. With this one, it's a bivariate normal distribution. See? See? Bivariate normal distribution. Bivariate. But it's two-dimensional. But we don't have to worry about that one. But I'm trying to say that you are trying to get the expected value, see, and try to draw the plane going through that one. That's what we were doing, see, going through that one. It's the plane, see, estimated plane. Estimated plane. That's the plane equation we give by, see, plane equation we give by EY given x1 and x2 plus beta naught plus beta 1 x1 plus beta 2 x2. You know x1 and x2 are bonus and this one bonus, the other one advertising, this is sales. It's right there. This one we can say advertising. And bonus. It's like that. So this is the expected value, expectation going through that middle part. When it comes to this assumption, that assumptions are completely that related to what? That error, 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 error. So this is what I'm talking about. This error on the other, this one, which I talk about error, that means that if you pick any point here, somewhere here, this is your y, and this is your EY. This is your EY. Okay, so I'm going to simply say EY. That gap is called the error. Error or disturbance, or called the noise, perturbation, anything. Okay. Error. That is y minus EY. EY or y given x. Okay, I simply add that one. That error, they say that error, see, error has the following properties. What are the properties? It's going to set in into something called acronym line. What that means? Line means linear, independent, normal, normally distributed, and equal variances. Equal variances has a name, homoscedastic. Homoscedastic. See, That means equal, linear means they're going to fit in into a plane. See, plane like this. See, plane like this. Independent means what? This bivariate is independent of this bivariate normal distribution. This bivariate. In this case, the bivariate because we have a advertising and bonus. Otherwise, if it's one, it's going to be just the normal distribution. Okay, bivariate. You are normally distributed. See, normal. See, normal. Bell-shaped. Bell-shaped. See, bell-shaped. Equal variance means this spread. See, here the spread from here to here, this spread from here to here and from here to here, the spread in each and every distribution is the same. Normally that's not the case, but we can assume those assumptions for us to work on these the equations. All the equations are valid if these are satisfied. That's why in the remedies, in the diagnostic, we're going to check whether error term going to satisfy all these conditions or not. That's why we have a graph for that one. When you're going to run a regression, you're going to see so many graphs. Those graphs are utilized in order to check this all the requirements. Are these requirements are satisfied or not? This is a very key part. This is a very heavy, because if not equal variances are not for the error terms, unequal variances, you cannot tackle this one the way that we tackle. You cannot use this formula. No, we don't use, we cannot, mathematically they cannot come to this, the proof like this. So they have to make sure these assumptions are, see, following properties or assumptions, see, assumptions. Let's see. These assumptions are satisfied under that. Now, that's what they were talking about over here. Simply independent normal, let's say they have constant means the same. Okay, so we talk about these inferences, we talk about, so here so far I talk about the individual and overall test. We saw that one, individual and overall test. Look at here, see, advertising. Look at the advertising, but the increase in advertising has no effect on sale. See, look at, they're gonna say in plain English. How could you gonna write this one? See, an increase, not the advertising, an increase in advertising has no effect on sales. Sales do change when advertising increases. Increase means, this means that the increases per given what? It should be like this way. The advertising has no effect in, see, advertising, see, has no effect for sales. Yeah, so advertising has already been included. See? Sales do not change when advertising increases. So this test we ran too, we saw that individual test. You can remember that one. See? Same way you can talk about the bonuses too. See, an increase in that bonuses has no effect on sales. Sales do not change when bonus increases. See? Beta 1 and beta 2. This beta 1, no, you can say beta add equal to 0. This one easily you can get it done by the table. You don't have to do by hand. These are doing, we don't go by hand. Or you can say, sometimes they ask another kind of a test. Look at this one. Increased bonuses do not affect sales. Rather than say increased bonuses. Sales increases when bonuses are higher. See, look at this one. See, sales increases when bonuses are higher. Here what they say. See? Sales do not change when the advertising increases. Sales do not change. Do not change. Here what they say. Sales increase. See, then you have to run this test. See, you have to run this test. How could you gonna run that test? See, those are the three things that you have to look into. There are three types of tests. There are three types of tests. See, then we can say, okay, so we say over here. So you can remember that if we related to this one, say that, okay, See, so you can say that you have see individual test. Under that one, we did this one. We were checking that whether beta advertising beta is beta 1, or you can say beta ad equals 0 versus its counterpart HA, which is beta 1 equals beta ad not equal to 0. If you write this one, you see, equivalently, you can say H naught is what? An increase in advertising has no effect on sales versus HA sales do not change. Do not change. Sorry, sales do not has no, sorry, sales change advertising has no effect. The other way around. I'm sorry, not equals means sales change. Not the do not. Sales do change. Okay. Sales do change. Sales change. The other one is no effect, but the sales change. The other one says sales do not change. Do change. When advertising increases. Increases. Look at this. See? So see, this one has no effect for sales. Advertising has no effect for sales versus advertising, increase of advertising has effect on sales. That means sales do change when advertising increases. So in order to run this test, since we have this one called, this here, this called what? The claim. This one is the claim. That's the claim. Somebody gonna say that advertising not gonna effect for the sales. Then in order to get this check, we collected data and then we run the test. You're gonna run what kind of a test? Two-tailed test. Two-tailed test. It's a two-tailed test. Two tails. That means that you're gonna have confidence in the middle and the level of rejection region on these two sides. These are called the rejection region, rejection region, rejection region. I'm gonna say this one RR. This one is an RR2. This one, this area. So when it's RR, how about here? What are these? This is here you have a confidence region. Confidence region. Let's see here. How much the confidence level? You can say 95%. The leftover you're going to put to this side, which is we're going to say 1 minus alpha. You can remember this is called the confidence coefficient. You can change that one. Confidence coefficient. See? It might going to be 95, it might going to be 75, 80, anything. If that's the case, you have alpha being left over because the whole thing is 1. You're going to divide this by 2, alpha over 2, which is 0.05 divided by 2, 0.025 going to go to this side. And this side also alpha over 2, 0.05 divided by 2, 0.025. Those two sides going to go. That's why we call the two-tailed test, because of not equal sign. In order to get this done, you can remember that we can look into the p-value. We can look into the p-value, and then we can get the answer. Okay, that's the one. That's the one way to have a look at. But here, look at when they were talking about this way. Rather than that, if you go to this test, Okay, sorry. This test, so you can say, okay, not this one. Then you're gonna go to the degrees of freedom. We don't have to do this by hand. Okay, we have done everything by program. But here, when you're gonna say this is the claim, in this case, this is the claim. You're gonna say sales do not do change. Here you say just simply change. You don't know whether change means like whether sales gonna go down or go up. We don't know. Here very particularly, very specifically, we're gonna say sales increases. That's why we're gonna set up like this. Sales increases when bonuses are higher. Okay. Here we simply say that when the advertising increases, sales do change. Change means like whether they're gonna go down or up, we don't know. That's why we set up a not equal. Here, this is the claim. But in one tail test, which is this called the one tail test, in this one, we're gonna have the only one side. See, individual test. See, it's a one tail. Here, the second one, this one, the second one, we're gonna say that H naught. I'm gonna say beta 1 or beta 2. Sorry, beta 2 means beta bonus equals 0 versus HA beta 2, which is beta bonus greater than 0. Now this is the claim. Somebody claimed like that. What that means? Equivalently, we can say H naught means increase bonus, increase that, you see, increase, you're going to increase bonus. See? Do not affect sales. Versus its counterpart, HA. That means you're going to say sales increase. See? Increase when bonuses are higher. That's the key. This is the key this time. Therefore, we're going to call this one tail test. One tail test. The material, that information that we need for the one tail test, not with us when you're going to run that this one. Let's say that when you run that SAS program, you don't have that information that we really need for that one tail test. And it's the one tail test. And then on the other hand, it's going to be, now we have a question whether it's going to be right tail or left tail test. See? Like this. Since it's a greater than, it's definitely what? Right tail. How did you figure that out? By looking at this now. Looking at this, see? Alternative hypothesis. While looking at the alternative hypothesis, you're going to decide whether it's going to be right tail. It's a right tail test because of because of the alternative H naught being this way. See, this way. Beta 2 greater than 0. Because of that, this one. It's a right tail. That means this whole thing is 1 minus alpha 0.95. This one is 0.05. You have to be careful. See, whole thing. One-sided. That's why they say one-sided. See, one-sided. It's just pretty much in a similar fashion. You can say sales decrease when bonuses are higher. Yes, you can put the less than sign, and then you do the left tail test. But when you run regression, regression on this one, let's say that we have a sales, we can remember that when we were running this one at a certain point with the, see, we need the CLBs. We did that one, see, Okay, let's say this one, sales, advertising, and bonus. For this one, let's get the data and then run this one and see what you're gonna have. Okay, so I'm gonna have this one. Then let's go to correlation, print com, 3D reg. I'm gonna go to this one. Okay, it's in the work directory. Oh, maybe 4 not found, but maybe four data. Oh, data out. Oops. Oh, oh yeah, this one. We changed the name. I'm sorry. This one. Restaurant. It's in that one. Okay. Okay. Then we go to the regression and with the CLB if you run. Okay. So you see the confidence interval, you see the p-value, you see the t-value, you see something here. These are the only thing that we have for the individual testing. Okay. So we are talking about this value. But the first one, advertising. Let's go to the advertising little bit. One more time. See, advertising, let's go. Advertising. Okay, advertising. See, it's a two-tail test. This is see, it's gonna be in accordance with the two-tail test. As I do, you have a confidence interval. See, two-sided confidence interval. It's a two-sided confidence interval. Okay. See, two sides. You have a confidence interval for beta node. You have a confidence interval for the increment of the advertising. Okay. So this one, beta add. So that one, see, at 5% significance level, 5%. See, so level of significance is 5. Alpha is level of significance. T value is 2.074. 2.074. Do we see that one? Advertising 2.074. 2.074. Why we don't have that one here? Okay, at 5.11 critical. Oh no, not the critical point. Don't worry about not that one. Not that one. I'm not talking about that. 8.98. I'm sorry. This one. This is this value. See, 8.98. How do you get the 8.98? They simply get this value. Okay, get this value. Estimate divide by standard deviation. Standard error means its own standard deviation. That will give you this value. When you find the probability more than that value is called this one. See, p-value. By looking at this p-value, you can make a conclusion. If it is a two-tail, yes. So this is about the critical value of this one. So we reject it. Don't worry about this one, not based on that one. Based on this p-value, we reject H0 because this is small. But for the second one, 8.98. Let's look at the t-value. Okay, look at the t-value. See this one. See 1.8562, 7.15, see 2.59. See here. This is the t-value. See, but they say that we reject H0, but this time make a more specific, specific conclusion. The listed t-value is for a two-sided test. For one-sided test, cut in half. Okay, you get like this. But what I'm trying to say, since it's one-sided, you get this value. T-value is okay. T-value is a certain calculation. T-value is simply you get this value and divided by this value. Sorry, this value divided by that one, you get that one. But if you get the probability more than this value, it's not that one. That's what I'm trying to say. Probability more than this value on both sides will cover this one. But this time you have to get the half of this guy. See, half of this one. Okay, because it's one-sided. See, it's one-sided. See, it's one-sided. It's not here, but you get that one, which is it's gonna be 0.08. 0.0008, 0083, the p-value. You're going to get the half of this one. Okay, make sure that you get the half of that one. So that's the reason that when you have a two-tail test, it's okay. This one, take it as it is. How do you know it is two-tail? Two-tail means not equal sign means two-tail. If you have a two alternative, not equal sign, that's two-tail. If you have a greater than sign, one-tail test. If you have a less than sign, one-tail test. Then how could you gonna get the results and interpret? You go over here, since we are trying to get this done using the p-value. This p-value is for the two-tail test. You need that one for one tail, get the half of that one and then compare. Then it's going to be not 0.01, it's going to be 0.08, 008. So 0.008 is again what? Less than, definitely less than alpha. Reject, you can reject H0 again. Okay. Reject H0. Reject H0 means this one. Reject H0 and you can accept the claim and say that the claim is true. Okay. So anyhow, what we are trying to do over here, this is the part that I have to explain to you, that half of this, whether it's a less than or greater than, these are two tail, one tail, I'm sorry, one tail. If greater than, right tailed. If less than, left tail. How do you make the conclusion? Go to the p-value, this p-value for the two tail, because based on this two-sided one, to get the one side, you divide this by half. Okay. Is by half. Okay. Remember that. That's what they were telling over here. So that one, this one, this we normally talk about the R squared, the proportional variance explained by the regression equation. Okay. Adjusted R squared, we talk about that one. We adjusted that one. Then we looking into the statistics. We look F, okay, we did that one. F based on the overall one. Okay. Then on this one, we went to the what? Now we're gonna check the what? Two regression model. You can compare two regression model by what? The partial test, using the partial test, not the overall test. I'm eyeing for three types of tests for this discussion. How could you gonna do that one? This means you go to that whatever the full model. Now in this case you have a full model. Let's say that with this example I'll explain. Let's say that in addition to the variable for advertising and bonuses paid, we now consider variables for market share and competition to be added to this one. We like to add these two. Medicorp market share in each area, largest competitor sales. See? So X3 and X4. Now we want to see the old model has R squared, this one. So we gain only 0.4%. And the T ratio for the two variables, this one, it does not look like we have an improvement, but we really need the F test to be sure. Did we gain anything by adding those two variables? By adding those two variables, did we get anything? See, we can add these two and then run the regression. See, we have a T values, P values, confidence interval. These are ANOVA table. Okay, then we have ANOVA table. Everything we can get it. See, we can get everything. We can simply go over here and you can add. See, I'm gonna add advertising, bonus, market share, competition. I'm gonna say, since I'm using the GLM, I have to say the parameter confidence level for parameters. That's called CLPARM, same as CLB in reg function. So let's do this one. I'm gonna run this one for all of them. 4 of them. See, look at. We pretty much get exactly what they have here. See? So you have negative 593. Let me see. See, estimate 593, 2.51, 1.59. You know these two, what these are called the sequential ones. These are also sequential. These are sequential, type 1 definitely. When you add these 3, 4, 1, 2, 3, 4, they will add to this one. We had that broader discussion the other time. Sum of squared regression means this one, this one, this one, this one add to that one. You know what these means? Those are sequential, one at a time. That means advertising being explained assuming that these three are already in this regression model like that. Anyhow, that these estimates, they are a standard error, t-value, p-value, confidence interval for each and every beta 1, beta naught, beta 1, beta 2, beta 3, beta 4. And then by looking at this one, you can write the equation. Okay, the model equation, anything that you want. And the ANOVA table, see. So the model, look at that. How could you know that this is 4? You know, we had that discussion on this one. How do you get that degrees of freedom is 4 for the regression? That depends on the number of regressor variables. How many regressor variables we added? 4. That 4 comes over here. Okay. Okay. Sorry. Yeah. So see that 4 comes over here. Okay. And then how do you get the residual? This one, n minus number of observation minus number of parameters to be estimated. How many parameters to be estimated? 1, 2, 3, 4, 5. 25 minus 5 is 20. And this is how much? Number of observation minus 1. 25 minus 1 always. And you know how we got this one. There are equations. We don't have to worry about that one. Mean square means this divided by that. F means this divided by that will give you this one. Mean square model regression divided by that one. So we have a p-value for the overall test. See, this for the 4 of them. And r square, see. And they say here something, okay, that's for the full model. Now say that this by adding these two, did we gain anything? See, gain anything by adding earlier. Look at the earlier when you have only two of them. You run 2 of them. Let's run this both of them together and then see what kind of improvements we have made by adding 2 variables. So earlier r squared is 0.85. Okay. Now what? Now r squared is what? See, 0.85. Pretty much the same number. There's no any improvement. Earlier r squared 0.85, 85%, now 85% too. That means they're not explaining any variation. Look at these two are doing a great job. Oh, see, when it comes to ANOVA table, see, look at this one, see, r squared, actually this divided by this is r squared, see, 85%. Now adding another extra 2 doesn't contribute that much. R squared stays at the same place. Look like the same place. That's what they say here. Sorry, I'm going to get rid of this one. We gained only 0.4%, okay, as a percentage, little bit, okay. T ratio for the 2 new variables are 0.57 and 30. It doesn't look like we have any improvement. But still, we want to test with the F. How could you gonna do that one? That one you're gonna do and say, you're gonna set up the test like this. You're gonna say the market share, and the competition's slopes or that coefficients equal 0 versus at least 1 is not 0. In order to get this run checking, you have to definitely use the partial F test. Partial F. Where is partial F? Let me see. There was the equation. There you go. You have to get this done by hand. This is done by hand. If you're gonna get the whole block, I'm not talking about one at a time. I'm gonna say 2. You get the 2 variables and see whether they are contributing to this one. While you have a 2 variables in the beginning, you add in another 2 variable. The newly added 2 variable, would they contribute in large scale to explain the sales in this particular example or not? You have to use this one. That means you go ahead and find the sum of squared error of the reduced model minus sum of squared error of the full model divided by how many variables in the full model. Sorry, reduce this one, full model minus the reduced model, see, K minus L, and then get the full model sum of squared error. See, that formula you have to utilize to get this done. Okay, let's see how that can be done. Okay, let's set this up. Okay, we have everything in the hand. Only thing that you have to plug in into that formula only. So this is what we are trying to do. This is called the partial test. Earlier we had an individual test. See, those are individual tests. This one individual test. Under that one, we talking about the individual test. Now I'm talking about the number 2 partial test. Means like I'm gonna set up and say beta market share. Okay. If you want, you can say beta 3 for that one. Beta 3 market share, which is beta 3 equals 0, or market share equals to the other month. Competition equals 0. None of these can contribute. If you want, you can call that on beta 4 versus its counterpart is not, we cannot put the not equal. Here you can say at least one of them. See, not equal to 0. At least one of them not equal to 0. How do you do this one? Do you have a p-value? No, we don't have a p-value to get this done. So for such a for such a test, we don't have. That's why we did this one full model. See, with the 4 we ran, and this one we ran. Let me see. Okay, I have to open. I think I'm gonna get rid of this. Yeah, see. So with this one, see, full model, reduced model. This is called the full model. This is called the reduced model. See, how did they become reduced? Because that you're gonna assume H naught is true. When H naught is true, these two are 0. Because of that, you get the reduced model. Okay. So the what's the formula says? Formula says your F value is nothing but, see, F value is nothing but, see, right over here for you to see clearly. For that one, F is nothing but, if that one, you need that value. F value is sum of squared error of reduced model minus sum of squared error of full model. This whole thing should be divided by its degrees of freedom. What is the degrees of freedom for that? That whole thing should be divided by sum of squared error of full model divided by its degrees of freedom. Sum of squared degrees of freedom is n minus p. P means number of parameters in the model. Model means it's a full model. Okay, full model. N number of observations. Or size of the sample size. Yeah, on the top, what do you have? They have K minus L. K means what? L means what? Let's look at this one, how they set this up. K. Up to K. K many variables are 0. 2 variables. That means number of variables in the number of variables being taken out. See how many variables being taken out. See, look at it. Go up to here. L means number of variables. See, x1 through xl. Number of variables in the reduced model. L means number of variables in the reduced model. Number of variables in the reduced model. K means number of variables in the full model. So we're going to take, they were divided by something called K minus L, capital K minus L. K stands for number of regressive variables in the full model. L means number of regressive variables in the reduced model. See, reduced model. So let's plug this into this formula and see what you're gonna get. You have to get this done by hand. So you go to the full model. This is the full model. See, this is the ANOVA table for full model. You go to the error of the full model, and its counterpart is on the top. It's a reduced model. For the two variable one, it's a reduced model. So we first go to the reduced model error, 181176. 181176. So let's plug it over here. It says C. 18 11 181 176 minus, let's go to the full model. Let's go to the full model and see. There, go to the ANOVA table. See, error 175855. Okay, 17. I'm gonna round 175855. 5855. Don't worry about the decimal. Okay, I dropped the decimal. Rounded to the that, because since we are dealing with large numbers. So the number of regressive variables, how many regressive variable in full model? Full model. How many regressive variable in full model? 1, 2, 3, 4. 4. How many regressive variable in the series model? 2. Okay, divided by, what's the full model that SSE? 175855 divided by number of observation 25. How many parameters to be estimated? Parameters. See, P stands for number of parameters in the full model. How many parameters in the full model? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5. Okay. So you're gonna subtract 5. That's your F. This is your F. When you calculate, you get 553.21 divided by 2 over 8793, which is 0.3026. 0.3026. This is the F value. Now what are you gonna do? Now after that one, you don't have any information on this table. This table doesn't have anything, but this being calculated by hand. Now you have to run the test. In order to run the test, you need something. What do you need? You definitely need, this has to be fitted into something called F distribution. Not the bell shape this time. F. This is F. For my convenience, I'm gonna put this on 0 to say observed. Observed F statistic. Okay, so statistic. If not, this value we can say observed. If not, okay. Observed state, observed F statistic. Okay, we calculated that one already. Okay, I'm gonna get that one here. Okay, 0.03. See, like a very small value. Very small value. See, now what? Let's say that I'm gonna go ahead and let's say here point F naught, not there. Okay, not this one, not this one, this one. Okay. It's right skewed distribution. Okay, F distribution. F distribution is right skewed distribution. It is a right skewed distribution. So F naught is 0.3026. Remember, F tests are always one-sided. F tests are always one-sided, and they are also right-sided. Right-sided, one-sided. So that means this whole thing to the right is your rejection region. Rejection region. See, rejection region. Whole thing related to rejection region gonna come in that side. And on the other hand, you get the p-value. Can get the p-value. So you're looking for p-value related to this one, p-value probability, f greater than f naught. You are looking for probability f greater than 0.3026. And this f distribution has two things you have to remember, two things. It's being characterized by two things. Degrees of freedom of numerator, I'm going to put n, comma, degrees of freedom of denominator, d. I'm going to write here, dfn stand for degrees of freedom, freedom in numerator. It's nothing but the degrees of freedom of what? It's nothing but whatever you had in that, this one here. See? See that one. That's the one, k minus l. K minus l, which is 2. And DFD means degrees of freedom. Freedom for denominator. These are characterized by those two. It's nothing but n minus p, which is 20. So those two are here. This is, you're going to write with numerator 4, 2, comma 20, like that. Now you have to find this probability. See, this probability. How do you find this probability? How do you find that probability? I need this probability, f greater than this one. See, how could you gonna find that one? Let's go ahead and see how we're gonna find this one. Okay, that's what we were talking about in 1. Let's I'll show you 1, this one, chapter 3. Here, see, over here. F, see, if you need the p-value, see, so if you need the p-value, see, for given, so given value, this is our p-value. P-value has been calculated in this program to the left. So that's why I'm gonna say probability of f distribution, prob f has been subtracted by 1 to get to the right, okay? I need this guy. I'm looking for, simply I'm looking for this region, this area. In order to get this area, they don't calculate that area. They calculate the area to the left. Area to the left. That's why I subtract. Whole thing is 1. The area under the curve is 1. That's why we call the distribution. It's not like a mathematical the function. Mathematical function, the area under the curve is not always 1. If it is always 1, that can be utilized as a probabilistic model. In this probability, that this area under the curve is as a physical interpretation. The physical interpretation of the face area under the curve is the probability, the total probability for occurrence of this particular event. So all the whatever the events that we are interested in this one. So this is the area. That area is called the probability. That is p-value, but they calculate to this side. I need to the left. I need to the right. They calculate to the left. Because of that, I'm going to subtract from 1. The total one is 1. Total is 1 minus. You give the f value. This is f naught. This is f naught. This is n degrees of freedom, numerator degrees of freedom. This is the denominator degrees of freedom to be supplied. I'm gonna give the input value as a F value, NDF and DDF, and make a data FP. See, my data name is FP. That means P value for F distribution, P value based on F distribution. Then I'm gonna go ahead and then give the some values. Cards 0.3026, 0.36. See, degrees of freedom for this guy is 10, 2, 20, 2, 20, and then close it. Then I'm going to go ahead and then print. Go to the data. What are the values I'm trying to print? These are the variable. I need to print the F value, the value that I gave. I need the N degrees of freedom, D degrees of freedom, and P value. Okay, let's run this one. This is the value you have. This is the degrees of freedom. This is the P value, 0.74222. 0.74222. So see, I'm gonna get this one, copy, and then even that paste to even the chapter 4 as well. Here's something here. Homework 1, oh sorry, chapter 3. So you got the value. This one is nothing but in this one, by running that one, you got this value. This value is 0.7422. Okay, 0.7422. Now you can say, and you can make the conclusion. Okay, since P value equals 0.7422 is what? Not less than, okay, not less than. Or you can simply say greater than. Alpha, alpha means level of significance, which is 0.05. We do not reject H0, in which we're gonna say beta market share equals to beta competition compete equals 0. We do not reject. That means definitely what? There's no impact from 10 at the level of significance. It's important to mention the level of significance, because you might be thinking by changing the level of significance, we can get this rejected. Yes, that's the tricky part. By changing this one, can we get this rejected? Yes, but we do not touch this one. There's a reason for this one. Level of significance means the size of the test. The size of the test and its counterpart is the power of the test. Okay, level of significance is, we have mentioned about that one at a certain point. Alpha is the level of significance. Not only that, it's the size of the test. The size of the test is 0.05 in this case. Okay, in addition to, I have something called another one, or this one we're going to call the probability of committing type 1 error. Type 1 error. You can remember what is type 1 error. Probability of reject H0 when H0 is true. You have H0 true, but you reject H0. Okay, that's the size. But on the other hand, I have something called 1 minus beta. I'll tell you that 1 minus beta is the power of the test. Power of the test. 1 minus beta, where beta is probability of type 2 error. That means probability of accept H0 when H0 is false. That's the power. Then the power and size should be the balance on this fulcrum. See, then they see power and size. When you this might gonna go up like this. Sorry. See, power go up. When you increase the size, decrease the size. When you decrease the size, power go up and vice versa. This is the power. If this go down, so you have to have a balance. This is 1 minus beta. We don't go to detail this one, but alpha at least we have a point of. See, now you might be thinking we can make it smaller. Oh, see, if you small this one, power going see large and large, no good. And if you increase this guy, it's getting lower and lower, no good. So you have to have a check and balance, like in that in the system that we have, like the executive, that legislative, and then judicial system, three system to have a check and balance. So pretty much this is the way that level of significance is like that, pretty much like in a courthouse, that when people have a like a kind of a like a, that when the judge decides that based on what has been written on the book, that we're gonna that define that this the crime has to be defined in that book, and then based on that one, what would be the punishment? That punishment is the level of significance. Based on that one, they decide whether the whatever you hypothesize in the beginning, you hypothesize H naught, the defendant is innocent versus his counterpart, defendant alternative is defendant is guilty. So they are building up the evidences, all the evidences, and based on that one, how could you gonna decide at the end of that? You're gonna say reject H naught at a certain point at the level of significance alpha. Level of significance is the that what is being written in that legal books, and then what type of punishment to be given for that kind of a crime, or let them go, that kind of a thing. You see, that's the level of significance. That can that be changed? Yes, that has been written by the people. They can arbitrarily change that one. That's why if you're going to change that one, you have to make sure it's not going to affect our balance. This balance has to be checked. That's the same thing going to happen in that courthouse. Same thing. So the level of significance very important. That's why I particularly mentioned about the level of significance at this level of significance, because I say that it's been compared and contrasted with this one. Then I'm going to say at that level it's been rejected. Because of that, these two are not playing any heavy role. See, it's been now convinced. It's convinced now. Earlier that by looking at the R squared, we saw that full model R squared has not been changed that much drastically. See, when it comes to here, see. R squared always same thing, 0.85%, even in the two two regressive variable model, even see R squared. See, they both look the same. Then we really needed to go further down and do something called a partial test. And the partial test is done through the way that I was explaining. Whatever that you feel like that not going to be helpful to explain, no, helpful to explain. If you have any doubts, you're going to set up like this for the test. Set up and then check. When you check this one, those are called the partial tests. The individual test, this one, it's a counterpart, the second example. And then we go to this, another type of called the partial test. And there's another one I talk about, it's called the overall test. Okay, overall test, we're going to set up everything equals 0, whatever that available, everything equal to 0 versus at least one of them not equal to 0. How could you going to get that done? By that f already available in that, not this f for the other f, but whatever the that regression model that you run. Let's say that you are interested in that regression model of this regression model only. Then it's if you're going to looking into that F2 and see whether all of these going to affect that or that affect to the sales, or this one doesn't matter, based on whatever that you're going to take into account. But here not like that. You're going to take into account two models and see which model is the best model. Looks like this model doesn't, see, for the sake of throwing variables, even though that you throw the variable doesn't make any sense. It's a wasting your time, money, labor, and it's useless at the end of the day. That's why we have to run the test at the primary stage Before you're going to go to data mining, before that one, you do the primary stage. If you know all these tests, the data mining becomes very, very easy, because by the time that we have decided to get rid of this one, then we're going to talk about that one in a large scale, call it using that these methods down the road, that selection procedures, forward method, backward, and the stepwise elimination method. Okay, that's another way to look at it. And a little bit go further down. Okay, further down, almost there. This one. Seems that prediction and minute time. Multicollinearity. Multicollinearity is a serious issue. Multicollinearity is a serious issue. Multicollinearity means when you have that regressive variable, what's going to happen? Instead of that regressing, see, interacting with this guy, sales and bonus, he's trying to interact with this guy too. Interactions among the regressive variables called the multicollinearity. That would affect our model at the end of the day, the power of the model. That has to be tackled too down the road. That means they are trying to interact with among themselves while they were individually interacting with the sales. See, you can find the correlation between sales and advertising, sales and bonus, sales and market share, sales and compete. On the other hand, you can find the correlation between advertising and bonus, advertising and market share, advertising and competition. If you are thinking about this, if you have any drastic impact changes on others, that any big impact from these correlations among these regressive variables, that has to be tackled. That's what we call the multicollinearity. We're gonna remedy that situation down the road, and then we have so many that ways to get this one. I'm trying to go to this one while we are going through the chapter 6 or 7, and then when we're talking about that one, I don't want to do this one at this stage because these are not being given for our test or that homework. So I'm going to just skip this one, but I'm going to come back to this. This one is very important later on, that in order to get the best model at the end of the VIF, variance inflation factor. That means they're going to run this one in different way. And we don't run anything. Those are, we can easily get those values by running VIF. See? When you say, give me the VIF, that will give you one shot. Okay. Sales, advertising, CLB, VIF. See? If you run this one, let's say we run this one for you to see. Okay. Yeah, okay. Variance inflation. Why I don't? Okay. See this. Where are they? This, oh yeah, there you go. See, variance inflation. It's already been given. So we don't do anything by hand. Okay, we have a formula, but we don't do by hand. Just call the CLB stand for confidence level of the p values, as usual. In addition to that one, this being added to that one. Okay, we can get those things done easily. So those things are we going to talk about, because in our homework, we're not going to talk about those things. In homework that we have, and this is related to this one. Lag variable. I think time series. If time permits, we're gonna get into the time series part later on. Overall put together, and then but multicollinearity we're gonna tackle again. Okay, so put that aside for time being, because we have to answer that midterm and then homework 2. So homework 2. So homework 2 we get into up to this point we came. We came up to this point. See? So we did up to that point, and in order to the rest, let's have a look at it that this slides and get a rough idea. Okay, in this one say fit in the curves to the data curve, different data. Since they say in chapter 4 the model was presented at this one, you can remember K many variable. I stand for the ith individual. Okay, it's not a big deal. There we assume linear relationship between y and x, linear. In this chapter, we find that this may not be, not be the true and consider curvilinear relationship between the variable, curvilinear. Instead of a linear one, we're gonna have a curvilinear. What are the curvilinear relationships? There are mainly three things we're gonna talk into about in this one. These are the x squared, that's a quadratic one, inverse, okay, inverse and log. Quadratic, inverse, and log. And this can just be that instead of taking x only, I'm talking about you're going to throw x variable, one variable, one regressive variable. Instead of that variable, you feel like I had to square that one. While you square, you still keep the x variable because of that you're going to take into account that the highest order. But sometimes you can go to the cube, but you cannot arbitrarily increase the power for the sake of getting a base model. No, again, it's going to mess up. It's going to affect to the power and size. And sometimes some situation 1 over x, and some situation you get the logarithms on x variable, or some cases you get the logarithm on both cases. Okay, so that's what we are trying to tackle over here. So look at in this one, telemarketing, this one average calls per day over 20 work days, months on the job. Data set telemark 5. I think that data already available on our the Brightspace in our the page. And if you go to chapter 5, see, I'm gonna go ahead and get the telemark data. See? I call that one polynomial regression, polynomial, because I'm trying to add x squared. Okay, so month calls, see, these are the calls, 20 calls, a number of calls, number of months of the experience. I'm sorry, see, telemarketing employee, this one average calls per day over 20 work days, months on the job, how many months this person is on the job. Okay, and then you can draw like a scatter plot. Okay, let's draw the scatter plot for this one. And content data from calls months. Okay, okay, let's get a scatter plot between these two. We don't have a scatter plot, SG plot. See, this one, not this one, not this one. I'm not talking that one. I'm talking let's get the scatter plot. SG plot, scatter plot. Okay, something like that. Data out. Data. Telemark 5. Library. Polynomial. Send the data out. Let me see. Libraries. Tele. Is that tele? Yeah, I call that one tele. Tele. And don't worry about the. No, I don't need to compare. It's just regular one. Title and plot this one. Forget about labels and this one. So the data out because daily, and it's going to be between between what and what tele, what are those output data, months and calls and months. Calls. Yeah, okay. So no, this should be the other way around. Calls should be calls versus that one. See, look at the plot. Look at the plot. See, see, if you're thinking like that, we can say fit in like a straight line. Straight line. It seems like a more of the data points gonna be above that one than below that one. So sometimes you have to have a balance. So on the other hand, by looking at this one, you can easily see that if you straight line, it always see that the higher the value of that, higher the months that he's been on working, with the working months, higher the number of calls. But that's not the case. When you have a more experience, the more months being in the workplace, you're not making that many calls because see, you have an experienced person, they not produce that much of work. We expect that way. We expect that when you have a more experience, you're going to produce more work. No, it's not the case because it's come along with the Pareto's 80-20 rule. 80-20 rule is that 80% of the work is done by only 20% of the people in any company. It's expected because when they're going to build up any company, they know that one. That's a rule. So here, look at more experience in the beginning, see, but later on settle down that ratio. See? So that means if you're going to do that one based on that, you think that more experience you have, more calls you're going to make. No, that's not the case based on this data. If you're trying to go with the linear model, it doesn't work. So that's why we have to go to non-curvilinear model. What is the best model to fit in into this one? Something. See, you're going to think about this look like a what? See, parabolic shape. See, parabolic shape. There's an increase in the calls with experience, but the rate increase slows over time. See, the rate go down. They go up, but go down, but very slow, getting slower and slower and slower with the more experience. See? They don't produce the best. You see, seems like due to several reasons. See? So that's why most of the companies, they were looking for sometimes that new bloods being pumped into the system to get the more profit at the end of the day. But anyhow, we don't go in that route, but I try to explain this one. So this one, you can fit in with the something with the add-in, see, not with this one. Okay. So since the equation is that R square implies that each month of the experience lead to this more calls per day. See? So this one means like this, see, every month, see, you are adding, see, how many, see, 7.7435 more calls per day if you're going to run this with linear equation. We first fit the linear equation and obtain this one. The equation which has an R squared of this one implies that it looks like a good model, 87.4. But the experience leads to this one. See, more calls per day. But can we get a more that R squared can be, see, look at heavily, see, increased if you're gonna go to a different model, which is the curvilinear model, which is in this case the polynomial model. Look at if you fit into something like this. That means R squared going up, see, and plus that see here 2. Can we increase that? How many calls they can make? See, increase of their rate. Earlier, not even one call. See, one more call's not being even been added to that one. See, if you're gonna add that the marginal number of calls is even less than, see, 1. That means that how many that more calls being added per day per given each month of experience, it's not even 1. But if you go to that R squared one, 2 calls. See? If you get a right model, that means we're not gonna go ahead and do anything, any adjustment for the employees. What we're gonna do, we get the data, we analyze the data. How do you analyze and then show to that their boss and say this is how it works? See, curvilinear. How could we gonna do that one on this one? I'm gonna go ahead and now I can run this one with the, instead of only months, I'm gonna run this one with the month and month square. See, month and month square. Okay. Yeah. See, proc GLM. See, okay. I'm gonna go ahead and run this one square. See, I have a month and month square. See, you know that's a quadratic form. See, so let's run this one. Let's see what you gonna get. See, if you want, you can run this one too. Reg, see, procedure reg and get that one too. See? Copy this one. Reg, reg model. Okay, see. Okay, this one. So we have data, then this one. Before that one, scatter plot, and then let's run data. Need the title. And we get the calls. We get the calls. This model would be calls. And the X would be months of experience. So months, how many months being on job. That's the same thing. R squared, 87%. We were talking about that one, 13.6 data node, 13.67.74. How many for a given and for a given extra month? See, each month, see, each month of experience leads to this many more calls. See? But it's not even one. See? So then we go ahead and then set up this data and like our modeling with the quadratic model, which called the polynomial. Okay, that's the content. If you want. See, here model calls months. See? Okay. That's a pretty much same thing. Okay, see. Let's see what you can get. Okay. You're gonna get the type 1, type 2 one. That in addition to that one, you can see their confidence level. I was asking about the confidence level. And then see their estimates. See true, false not. See for each month of experience, you're gonna get like the 2 more calls being added. See, you're gonna set up like that. So that makes sense. Okay, that earlier we didn't have anything, but if you get based on what the work that they have done, we collected data. We should be very that be fair with their collected data, and we cannot just fit it into a linear regression and get the answers and then go and produce to their bosses and say, hey, it seems like they're not producing anything. It's not fair. So that's why when we're gonna run that do the data analytics, we have to make sure we're gonna come up with the very best model. They are might not going to be a perfect model, but the best model. See, it's been already drawn. See, like this way too. See, this way too. See. So on the other hand, if you want to do this one in a different way, then add in this one. See, I did this one a different way. I got the data out. See, call data out dot call data. Okay, I'm going to create a new column for that data. Okay. See, for the data, see, set up the data out, go to the tele, and the tele data, you're going to say the call data, see, and month square, I'm going to call the new one months time month square, see, and that one I'm going to add over here, month and month square. See? So I'm going to run the whole thing. And you get the pretty much the same answers. Pretty much the same as, see, now I call the month square, month and month square. Rather than putting like this way, if you want, you can do this one first. And then that being given to month square. And then see, I got the data. Sorry, I got the data and set that back into that my data. See, set to that one. You do this one, get the data, and you set this one. See, all data. See? You cannot get this one, set to this one, and then call this one what? See? Call data. Then you're gonna recall call data, not the anymore tele data. I have given a name for my data. See, call data. Okay. Data out. So if you go to see data out and the data out. Oops. I gave a name for that one. I set to that one and then see. Go with this one. Then if you want to draw that graph for that one, is G-plot, and then set up the regression. You can draw the scatter plot only. I'm gonna do the scatter plot for the degrees 1 and degree 2. Look at what's gonna happen. G-plot. Scatter plot with the regression line. See, I drew both. See, straight line, assuming that you can fit in into straight line as well as the other one. See, the one. So they were done like this. You see, linear one, curvilinear one, both. You're gonna say degree. See, so this. See, when you get the regression, with the regression, it's gonna come with the scatter plot. Okay, why cause this one? You can draw that one too. These are two different regression. One for the linear regression, the other one is a curvilinear regression. And these are the under this curvilinear, this is a polynomial. Polynomial means it's like that same thing being squared. See, same variable gonna appear in a different degrees, different powers, different degrees. Same thing. Okay, I'm not adding another variable. Same variable being the modified and then added back into that one. That's what we were doing over there. See, so in a linear, see, linear regression. See, regression. See, you can say y equals see, b naught plus b1x plus you can say b1x squared. I'm sorry, this one not right. It's not connected. So I'm talking about this one, curvilinear. Curvilinear regression. Then you can say y equals beta naught plus beta 1 x being remodified and then added again x squared. See, beta 2, beta 1, beta 2. See? Or b1. Okay, this is called the polynomial regression. Polynomial regression. Polynomial. See? This one called the quadratic regression, because the quadratic means second power. See? Highest power of x, highest power of, we call the degree of x equals 2. See? equals 2. That's why we call the quadratic. You're going to get the parabolic shape. Parabolic shape. Okay. This one, well, some people, they're going to go to b0 plus b1x plus b2x squared, d3x cubed. Up to that point you can go. Then you get the cubic regression. The highest power is 3, the degree 3. See, that's a polynomial. Or under this one, second one, inverse regression. That means you can get b0 plus b1. X has been written like this way, 1 over x, for a certain reason, because of the shape. That's the inverse regression. For the third one, we call the logarithmic regression. Then you're going to get y here, v0 plus, I'm going to take the ln of x, ln o, I can write o, y equals b0 plus log x, okay? ln means natural log logarithm, or log simply we call the log, and log means that's the logarithm, okay? Either way, there are 3 types based on mainly. Or there's a fourth one that is another part of logarithm 1. A, B, O. In both one, I'm gonna get the ln or log on both sides. Log y equals b0 plus log x. You can write like that way too. Those are the 3 continuous ones. So based on the given data, you can, it's done. See, that's why they say that next one, that on this one they were talking about, see, and increase that one. Then you saw that there's a r squared has been increased. So many things you saw that one. See, you can testing, see which has to be utilized, whatever the data to. See, use the linear equation, use the quadratic equation. That can be tested by simply going to that p-value of that guy. Whether you're going to go to this one or that one. How could you going to do that one? Beta 2 equals this one. See, beta 2, see, b2. See, that means b2. See, this one. See, negative, this one. You find the p-value related to that one. So here, so if you want that one, see, p-value, p-value, whether this equal to 0 or not, whether this be playing a heavy role or not in explaining that sales. Right there. Sorry, not the sales, in the number of calls. Okay, calls. And you can test that one too. And see, you would return this one. Or in some cases, see, some cases you can get to subtract that one. See, okay, some cases reciprocal transformation means that inverse. See, that example, look at that. We have to intercept the between gas mileage and the car's horsepower. See, car's horsepower. See, let's see that what's going to happen. Look at their graph. Look at the graph. So, oh no, I don't. It's all right. Okay. So let's go to here. So let's go to the this one we did. Okay. Daily data, we did that one true. We drew that one. Then inverse polynomial regression under that one. I'm gonna go to the see this data, MPG, HP, horsepower data. See this one. All right, this one. I'm gonna run that one. Let's see the data. I'm sorry. Let's see the data. See, and highway horsepower and the highway mileage. Only these two, being that taken for different kind of the different make of the model, the make and model of the cars. And then if you go to the scatter plot, let's go to the scatter plot on that one. See, look at the scatter plot. You cannot even think of that regression, the simple linear regression. Straight line doesn't fit in. See, if you do that one, very unfair. You see, you have to make sure at least get there as much as to here. See, it goes like this. The higher the horsepower, the lower the highway mileage is. Just keep going. That's how it works over here. See, it goes this way. Okay. Is that right? Should be. When you have the higher the horsepower, lower the highway mileage MPG. Yeah, that's right. See? But it's gonna consume so much of that gas. Consume so much of gas. That's true. See? Look at that. So for that one, if you try to fit in this one, this look like what? What is this one? This is a one arm of what? One arm of the something, some kind of a mathematical graph called hyperbola. That's a one arm of a hyperbola. See, you can remember this one, this arm, this one, and this one is the other arm. What is this? These are the rectangular hyperbola. If this is y, if this is x, y, if you multiply x and y together, that equals to 1. That means y equals what? 1 over x. 1 over x. There's a one arm of that. So there's a one arm of the rectangular hyperbola. But normally the hyperbola like this shape had been rotated to get the rectangular one. So since we have that one, what we're gonna do, we're gonna fit that one into the 1 over, see, I'm gonna say, first we're gonna draw this plot 2 this way, see, look at, I'm gonna call that data, so Sumit, okay, then this one and this one, we did that one, look at this one, G plot, get this plot. I think it's G plot, I think something missing over there. No, yeah, G plot can get it here. With the G plot, even that you can get this way, but make sure that you're gonna see, if you use that one, you're gonna say highway mileage y, this one equals to 1. Then you can get this here. If you want a new column, again, like earlier, see, if you want to call that data, see, so you set this one to what, see, I say HP inverse, I'm going to say HP inverse, rather than putting over here, I set this up first. See, I set this up first. I'm going to go to the data, see, go to data, see, and then Sumit data and put it back into Sumit data. Okay, let's run this one. This is, see, it's already created another column. See, it's created another column. HP and HP in. See, earlier we had only 2 columns, highway and PG and HP. Now you have HP in. It's been put it back into the same data set. See, put it back into the same data set. Set to Sumit again. See, and that one I'm gonna use with the model. See, run regression with that one. one, you know, number of regressive variables in model one. See, this one, you know, this value, see, 13.63. See, this is for beta node, this is for the beta one, this is for beta one, beta one. So, see, regression of this one on HP yield highway, see, this one with R squared, this one. This does not fit too well because as horsepower increases, mileage decreases, but the rate decreases is slower for more powerful cars. All the other models, including a quadratic, might work. We regressed highway on this one. See, it might work, but we regress like this way. See, most of it this way. Like that. So that's how you're gonna get the inverse one. Sometimes if you feel like that, okay, I'm gonna go ahead and get this done using what? Using the quadratic one rather than inverse regression. You can get this done. I created this one here. Okay, let's try this one instead of this one. Okay, I'm gonna try something here for you to see. Okay, copy this one. I'm gonna go ahead and run this one and see highway. And can we write the HP 1 over HP in? See, 1 over HP horsepower here and try to run like the inverse one. See, okay. The model rather than creating that one, I straight go to that one. Same way I did for that here. Excuse me, I did two ways. One that I just did as it is, months and months squared here. Then I got the square month square, set it somewhere and then put it back into the data set and create another column. Okay, called the month SQ. Okay, and then that one we utilize here as a second variable. Okay, same way that instead of doing that one, you can we go straight and get this done. Syntax error. That's why I did like that. You can give a try and see. Okay. So I did that one separately and I'm getting over. Okay, this one. Let's see what get the regression line. See, if you get this regression line, that's like that. See, that's another way to that further that just a regression line. Increase this one. Sounds like you can use the graph for this one. The mainly that I'm not interested in that one for time being, even though I keep that one with if something necessary, we can utilize that one. Other than that, if you're going to focus on that that log transformation, the next one, yeah, that the log transformation. Okay, don't worry about this one. To diagnostics. Okay, yeah, don't worry about this stuff. Okay. So here, log transformation, as I said earlier, then now you can do the log. Let's say that why we doing the log for this one. See? So why we really need the log. Another one is this one. Let's say that this one. See, fuel consumption is that fuel count 5. This one. See, fuel consumption per capita, state population, area of state in square miles, population density. See, if you get the fuel consumption versus the density, see, look at here. It's been scattered here. You cannot do nothing. Looks like a vertical line. Vertical line, there's an extreme value over here too, an outlier. There's no way you can go like this or like this or like this. See, curvilinear, inverse, regular, simple, quadratic, nothing gonna work over here. That means this has to be expanded. See, is to be expanded. See, the graph has one point, DC on the right with all other clump to the left. It is hard to see what type of relation there's until the adjustment are made. Here, take the natural log of density to pull the extreme points back in. See, density. See, density versus this one. So if you go ahead and then look at the data, get the data, this data, the logistic log regression. Data over here. See. GDP. Oh, let me see. No, it's not the right one. If GDP is that the right one? Yes. Yeah. Oh. No, I think that's not the right one. Fuel con 5. Let me see. There should be another example. Yeah, let's go to this one. I think let me see what happened to this one. Okay, I think fuel con 5. Log regression. GDP. Let's try that one too. This one here. No, messed up. I need this to be. So log reg, you can say log reg, this one log reg 1 for that one, this one in GDP. No, I need this data set. I hope that data set we have is fuel con 5. Fuel con 5. Can see that one. Let me see. Yeah. So welcome 5. I'm gonna go ahead and add to this one too. Make one assignment. Okay, we have a data. It work on Indicop. Okay, I'm gonna that one too. Before that, I'm gonna save this one. Save as to go to data. Data. CSV. Okay. This one. Yeah, data index system. Have that one. You can see that one to see full config. So that's that one. Let's get full config. Work on. Why it's not there? CSV. I'm gonna check that. It's not the data 4.5. Okay, I know the reason. Okay, this one. Okay, let me see. Okay, this one. No. Why? Okay, I know the reason here. So reason this one October. Because it's not in the other folder. Okay, work on pop area, work on this one. See. Okay, then we can draw the scatter plot for this one, Volcon versus density. For this one, let's see. Okay. So we can say X should be density. Density, the other one, Y should be compound Y. Oops. Log rate one. Okay. Log rate. Okay, it's in the work one. No, log rate one. Yeah, work one that should. Why it comes? Scatter. X, scatter density work on. Okay. Density, what happened? Density. It's not density. What happened? Density. Density. You have a density. What happened? Status sheet doesn't have a density. How come? Which one we talking about? See. Volcano population area pop den. We call the pop den. Okay, let me see. that data. Why we don't have that data? Worldcom area, Worldcom area. So why on this one? Fuel consumption, Worldcom pop area, pop dense. Pop we have, area we have. We are missing that in this data. I don't know. How come? Yeah, this is not there. But they have drawn this one versus density. There's something wrong somewhere. See? Population density for the this one. See, plot of world consumption versus the density. It's not there. Okay. Anyhow, yeah, that might be the reason I think that I skipped and go that one when I was doing earlier. Okay. Anyhow. Yeah. Then no, this doesn't work. Yeah. Okay. Let's go to the other one and import. Let's try this one. Okay. Let's try this one. Then both being that, see, something like this. But here that we're gonna do that. If you do this one, that get the like a logarithm on this one, this will be that spread out, and then it come up with a nice picture. See, log density. See? Then you can fit it. Linear log regression, you're gonna compare and contrast later on. See, R squared adjusted. Look at the R squared has been improved. If you're gonna add the log den. But anyhow, in the data set, original data set, we don't see that one. Okay. We don't see that one. Maybe, let me see. I'm going to have a look at it one more time. MPG, MPG, MPG5. Let me see. Welcome rather than that one, MPG5. At the same data set. No, that's for the other one. No, that's the data. That's okay. So let's look at that, getting this data set. Okay. Imports. See, imports and their GDP. Okay, let's the plot for that GDP. See, imports versus GDP scatter plot. See, look at that, means this been expanded in this way and this way, both ways. See, not one way. See, it's been see, clustered here, somewhere here. That's why we're gonna take the log on both sides. See, I'm gonna take the log on both sides rather than doing this one. I'm gonna set that one earlier and put this one. See, log rate. Set to log rate. See, log rate. Get the data, do this one, set it to log rate again. What I did was I get the log on GDP, log on imports. Okay. And I'm gonna run this one. See? Because of this data being clustered on one place. See? See? Now I have log GDP and log imports. Log in, I call that one login. See? Log imp and log GDP. So those will be added to as a two columns to the same data set. And now I'm gonna run my scatter plot and see, and extend this one. See, log imp versus log GDP. See, nicely spread out, and then you can easily fit in into like some kind of a linear regression. It's been linearized. It's been linearized now. See, now you can get the model. See, regression. Import GDP, You can, I'm going to run here 3 of them, okay, to compare contrast. See? Compare contrast 3 of them. What are those 3? One linear one for the original data. See, model 1. Then second one, see, model 2, log GDP, log imports. See, and the model should be model 3, variable imports. Okay, let's see what are these 3. See, imports. Imports to GDP, log to log, and important this one. See, look at, it's a regular one. Imports and GDP, and log on both sides. And import, I don't do anything. I'm going to do expansion only on the GDP, and then compare and contrast. See, these 3. That's the kind of a discussion we are building up over there. See, so in that this one, unfortunately, we couldn't run on this one because the data is missing the density part. But if you go to that one they were comparing, contrasting, and then go to the next one, imports, the gross domestic product of the national income and dollar amount of the total imports for 25 countries was obtained from the World Fact Book or World Bank Book. For both variables, low values clumped together and higher values spread out, suggesting log transformation for both. See, low values clumped together and then high values spread out. So see, because of that, you're going to take the log for the both. You saw that one, what we did, and look at here. See, look at this one, imports versus GDP and log. See, look at the R squared. You can see that on your this one too, the same results. So R squared, if you go to R squared here, see 0.83. See that one log imp. Okay, that one, see 87 and 87. That means regular and only log 1. Okay. Okay, log 1. Let's see that which one related to this one. See, but for imports, see, residual for imports. This one log GDP. Log GDP R squared. Get R squared. Log GDP only. The other one, see, log GDP and the dependent variable intercept and everything, and the X variable they're going to show over there. The third one, look at GDP. I'm talking about here, see, GDP, log GDP, log GDP. So they're going to show you only the X variable, okay, not the Y variable. X variable, GDP only. See, only. Then you have that R square, 0.8770. 8717 means 87 to 87.2. And the next one, if you go to the next model, is that log to log. But here only that they show that only the X variable, okay? That means, well, you know, normally that's the coefficient of this guy being shown over here. That's the beta naught, okay? See? Beta naught. Sorry, beta 1. Beta 1 log GDP. This is beta naught. Okay. As I shown earlier that in that the discussion, I showed that one. So then related to that one, this is R squared, 0.83, 83 something. See, 83 means 84. They were not comparable. Okay. Now what they're gonna do? Here again, they go over here, and then you put what? You put the log GDP, and then you take out the log on the other one. Look at what happened to R squared, drastically going down. 37. See, you might be trying in different ways, and then but out of these 3 models, you're going to see that which model would be the best one for the comparison and contrasting. They cannot compare these 2. But in order for that side here, they say R square compare different things. See? For the no log model, is the percentage of variation in imports explained. For the second model is the percentage of variation in LN explained. Okay, second one. Okay. How much imports being explained in over there means 87%. Okay, R square for no log model. No log model, see, so much being explained. But see, 87% B, you think that the imports that much of imports being explained. See, see, no log model means imports being variation in the imports being explained. The other one only 80% being explained, the variation in log. If you converted the fitted values of the second model back to imports, you might find the log model better. But that means that that's what they were saying here. If you converted the fitted values of the second model back to imports, you might find the log model better. That means that they say that don't do this one. They say that don't do this one. They don't do log on the import and just take without imports and then compare and see how these two gonna be. Which one gonna be the best? Compare with not that guy. Compare with this guy to that guy doesn't make any sense that much because the R squared is completely that close to each other. But you saw that in a scatter plot, only one factor cannot be taken into account at the end of the day. It's like a very, very broader discussion coming to the picture at the end of the day. Because you saw that in the scatter plot, how they've been spread out if you don't do this one. If you don't take the log and log on this side, that you saw that all that most of that lower value clump at the lower y and the lower value always clump at the around in the neighborhood of the origin. And the other values, that extreme value being spread out. But that has been remedied by taking log on both sides. See, like remedying log, see, both sides. See, both sides. See, taking log on both sides. But they say that when you take like that, if you compare with the other one, that doesn't make any sense. But they make sure to take the log out of this one and then compare and contrast and see which one's going to be the better one. So you can try in these three different ways. That's what they were doing over here. But when it's come to the homework one, that's very easy. I think that if you go down that one, you can see that if you go to this data, second data set for the UN data set, they say go to the fertility and then this GDP. They say first one, you're going to go to the fertility and then make the Y on the GDP. See, you can get the scatter plot. See, run the regression. See, and they will take in the both log on both sides, one at a time. PP, GDP versus fertility. And then see regression to regression, scatter plot to scatter plot, fertility versus, see, per person, that GDP per person, see, and this is the fertility, that particular data set. Very easy, see? Go here. PP GDP has been given, this is fertility. Then let's say that for that one, let's draw the scatter plot and see fertility and this one and see why we are trying to take the log. See, they were clustered here. See, they were clustered. You have to expand. See, how do you expand? You can take the transformation on this one, What is the only transformation we can think of? Log transformation. Log transformation. See, you saw that in the previous, that in our description in the chapter 5 material, you can do the log on both sides. See, this way and expand it. So, see, fertility PPGDP. Then what? Then we're going to take the log. See, you can straight take the log. Okay, go to the log fertility and the log PPGDP. See, PPGDP, log of fertility. Okay, now give the scatter plot of log versus log. Look at that. See, now see, they've been spread out like that. So if you run this one, see, that's what they were telling to get that one to that one. Gonna run the regression for that. And now if you want, you can run the both regression together. No? See, this is the other one. See, you can see the R square. See, R square. Look at here. R square. See, 21%. At least it's been improved. It's been improved. Okay. Can we think about? Okay. Can we think about the third one? Third one is what? Let's try something. Okay. I'm gonna try something here. I'm going to take out the way that we did like earlier on Y and then try another one, another set. And say progress data out, then PPGDP, rather than this one, I'm going to say log. You can say log of fertility. Log fertility. If we create that one, no, we can just simply say the log. See, PPGDP, log of this one only on Y and then reg. Log fertility. I'm gonna try this last. One. No, what I think I'm doing not right. I wanna have this one scatter plot and that one together. Sorry, the one is scatter plot, the other one is the regression. That's how I know. This one of them is enough here. 3 of them. I'm gonna run scatter plot here. Another one. The scatter plot for this one, X just fertility, and that one. Then their regressions are without log, both logs, one log. Okay, good. Okay, this one, this scatter plot. This one only. So you saw when both how it works. And on the other hand, let's run 3 of these one regression and see how what kind of improvement. Even though they haven't asked that one, let's run and see. Okay, look at this one, 0.21. This one, see model, just without log, see, log to log, 45. See, only one side log. See, only one side log. 22. In any way, see, you can compare with one side only. Then you might be thinking, okay, why we not gonna try this way, the fourth one, only for, okay, the Y on this side, the log on fertility, but not on this one. Okay, let's try that one too. Copy the fourth one, fourth option. Okay, see, I get the log on fertility, no log on GDP per person. So in a similar fashion, let's look at the one, this one. Oh, sorry, copy and paste. And there, this one log model would be Y is log GDP. That this one, no, I think we made a mistake earlier. Let me see, this is consistency. No, both. Okay, they don't have. Here, second one, we have a log on both. Okay, log on both, that's right. The third one I added the log on Y, this one, log on Y. Log on Y here, this is issue over here. No, that results not right. Log on that one, not on this one. Okay, I'm gonna compare all these 4. Later on, no log on PPGDP, log on this one. Okay, it should be like that. The fourth one, log on this one, no log. Log on their Y, No log on this one. If you can run the scatter plot and see how it works. And mainly, we run the 4 regression and then see what happened to R square. See, still look, there's no any big improvement. So let's run all these 4 together. And then see which one's going to produce the best one. Best results at the end of. So there's nothing, see, 21%, very low. Okay, then both log, we get 45%, see, R square, or adjusted R. Then see, 49%. When see, but sorry, linear one, 49, see, is that linear one? 49, okay. Then look at this one. The other one, 49. GDP. Okay, this one. No, not this one. Sorry, I'm looking at the wrong. See, log PGDP. Log PGDP. They all have the same thing, but not here. Linear. So it's both log. No, this one no log, this one log. Okay, compare with that one. Okay. PPGDP, no log, this one. Okay, it's the 4th one. To relate that one, 22. Okay, the one before that one, log to log. Log to fertility. Log to fertility, 3rd one, see? Log to fertility. Y, X, Y, Y log. That one R square. Let's check R square. 49, see? This one. I'm talking about this one. Y log. See? That's this picture. See? Sorry. See? Log to log. No? This one. See? It plot for this one. This one is the 4th one. This one. A fitting curve. I'm talking about this one to this one. Fertility. Okay, that results on the top. And if you go to this one, log to log, this results R is 45. And if you go further up, see, nothing, no log transformation, its results is here. See, 21. So the first one you can out. And log and this one, log and that one, see, if you get out of that one, you can see this one playing a more role. See, R squared is, see, move for that one. But when it comes to that, even though R squared is that higher, this one 45 can be compared with, as we did earlier, without log for what? Without log for this one, X. Without log for X, see, sorry, this one, without log for X is playing a heavy role. Can you remember here? We say, okay. So this one, see, versus that one, log to log. Log to log, and without this one, can compare, they were close. But here go the other way around. See, without log and both logs, and 1 and 2, 1 and 2, very drastically change. See, first one, 21, second one, log to log. You can easily compare 49, 45. But even before, because of that reason, they say that one of these log can be compared with the one without log for the X. See, Model, if you second back to the imports, you might find the second model, fitted value, the second model back to the log model better. See, that means earlier, see, not in this one, homework chapter 5, we was talking about, see, third one, without log for y. So without log for y, this one, the last one. But this time it doesn't play that any heavy role. You cannot do comparison. So it has like the fourth one, without log for y, r squared is very low. So because of that, you do the, see, you try all these four and then do the comparison and contrast. Yeah, that's how we have to do. Yeah. So they're not asked for that one, but if you want, you can add the more that can you remember in that assignment, they were asking you to do, let's look at the assignment real quick. Then oh, I'm gonna get this one. Better fit or log or linear. Just they were asked about the log or linear, but when it comes to the log one, so they wanna tell you to just simply say the set of PP versus this one. See, very easy. It's not perform regression using both log and linear transformation of the data. Or I have provided log transform data for PP, GD, and fertility, which are respectively log, and log. See, they were already in the system. That's why you don't have to call you don't have to create it. They were already created. Okay. They were created. That's why I didn't create. I just recall the names only. They were created. So they if you want, you can get all the four and then compare contrast. And on the other hand, that we can continue this discussion even for tomorrow. Okay. So on the other hand, for the midterm test, that if you go to the midterm test, that it's pretty much same like the number one test. See, number one homework. Sorry, same thing. Homework number one, only thing, we have a different data set. Oh, then see, okay, I can add this one too, that with some description, you can see that one. Okay, what I'm gonna do, I'm gonna go ahead and add that one to here. So I can add that one, that little bit revise that one. I can go to homework to here, midterm exam. I'm gonna say add existing. I'm gonna say midterm this one, plus I have to add the data set too. See, I'm going to keep that one. So it's called the midterm. Yes, midterm. Where did that go? I don't see that. Where did that go? Oh, here. Sorry. So I'm gonna get that one to right below this one. Midterm. I'm gonna call that the midterm, and you can see that the midterm exam homework to see the more detail on that one. Plus, I'm gonna go to the midterm exam, go to assignment. So I'm gonna add the data set here. Okay, I'm gonna add the data set. Go to week 2. Okay, yes, the week homework. Or either this one. I'm gonna add to both of them. Okay. Then week 2 assignment and homework 2, and here too. Week 2 assignment is the one they created. I think better off to it's like that they create. I'm gonna add to this one. Okay, go to assignment. That's the only one I can edit. I can get the data and then and save and close. Save and close. Then. You can see week 2. Week 2, if you want to go as a student. Week 2. Here, midterm, okay. If you need the more the explanation, know that more detail on that test exam that you can get from the midterm. So easy. So you can get rid of that one. That one, that's good. And then, as I said earlier, that this one only thing. So instead of having that the cast data, we have a hard data. So same thing. See, generate a scatter plot matrix and briefly explain the relationship that the height, weight, diastolic, blah, 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 and t-test the same way that we did. And this time provide the estimate and standard error only for the mean. Okay, both cases, no variance this time. It's easy. And then you create the first the bilinear regression model, bivariate regression model. For the second one, continuous variable X with the next best correlation with the dependent variable. See, for the first model, use a continuous independent variable X variable that exhibit the best correlation with the dependent variable. That means you have to get the correlation matrix and see which one's going to show the best one. That's the one that you're going to fit in this one as a X variable to predict the cholesterol level. Y would be cholesterol level for sure. X would be the one with the highest correlation. Then second model, you're going to get the second highest highly correlated model with the variable with the cholesterol level. And then explain and support the difference between the model from steps Y and B. Create a multiple regression that uses all of the continuous variables. Explain and support the compare and contrast, so that we can go through that one tomorrow. But I will just a little bit show you that in terms of specific. So you go ahead and get your data, hard data from wherever you have that one. Okay, you can save and get it. And then you can easily get the scatter plot matrix. Okay. See, these are the variables. See, these are the variables. So you have to be careful. Okay, this one, I'm expecting something. Another thing, okay, you can see this data set very clearly. Missing data. Missing data. Do we have to do anything for missing data or not? We can discuss about that. See, missing data, how to tackle missing data. See, you can see missing data, especially age at this one. See, age at death, missing data. Where else we can see missing data? Let's see. Not the variable, not these ones. They were not missing here too. Cholesterol status. Sometimes we don't have info. See? See? Age at death. The other one. See? So smoking. Missing data. Missing data. Missing data. Missing data. Missing data. See? Missing data. You have to see that what we are supposed to do for the missing data. Okay. See? If you want to count the missing data, you can count too. See? See? So, see? Imputation, we're going to do the imputation. Some kind of imputation. Missing data pattern, you can see that one. We're going to do this one in detail tomorrow, okay? So let's say that let's go ahead and get this scatter plot. Okay. Scatter plot matrix, let's see how it looks like. the remedies, we can talk about other remedies. We count the missing values. We can count missing values. From this one, the numeric variable missing value. That's going to happen. How many missing values in each and every one? See, up to there, there are two: smoking and the cholesterol, and age at death. No missing value, but I saw the missing value. Age at death. Age at death. This is what age at start. Okay. So why they not gonna show the age at death? Okay, we didn't give that one. No. Okay, there's another variable. Let me see. Okay. So age at start, age at death. Okay, let's have a look at it this one more time. So bilinear. Okay, mean. Okay, sorry, this one. Height. Please explain the relationship. It generates scatter plot between height, weight, diastolic, systolic, MRW, and cholesterol. Okay. Height, weight, diastolic, systolic, MRW, cholesterol. Okay. Then missing we need for that, because I saw that the age at death. Hard data. See, age at death. See, sin data. Smoking. See, missing data. Yes. In the numerical variables, especially that age at start. Age at start. No. They give that information only for two. See, cholesterol. Cholesterol. Okay, let's see. Age at death course. Age at start. Cholesterol status. No, cholesterol level. This one. See, this one. Missing. Missing. Age at death. Missing. Smoking. Missing. Age at death. I think we can add that one to age. At death. See, so many missing. Age at death 3280. Age at start nothing. See, smoking, cholesterol 152.36. Missing in smoking. MRW, weight, height, systolic, diastolic, even. They have some missing values too. 666. Height and weight. Let me see, height and weight. Height, weight. Do we see the? Yeah, I saw someplace. See, height and weight. See, missing value. Those missing value. See, how many missing values? See. So later on we can take into account. See, missing value can be taken out. See, by putting that 0 or the mean value. Okay, average imputation. Okay, that one I'm gonna do that. See, you can see in several ways. There are several ways you can remedy that mean with the missing value. Let's talk about that one tomorrow. Okay, and then just finish this one and the both, and then we can talk about a little bit chapter 6 too, that and then go through that one. But for time being, just work on homework 2. Then we can jump into the midterm, and then especially remedy that. If you have any method to remedy that one, that's okay too. See, you can get a idea from this one. STDized, studentized, that called the studentized. That's a one way to get this done too. There are several ways we can get this done. To this set, we can thoroughly go through this one and the homework too. That by answering all the things one by one systematically. I'm gonna do that one tomorrow by putting all the labels and everything, numbers and everything for you to see clearly. So I'm planning to wind up over here, and then do you guys have any question, anything that I do, if you want me to add? I can have this one sometimes. Okay, hold on. Okay, sure. If you don't have anything, okay, I'm gonna let you go, and then you guys have a good night, and then see you guys tomorrow, and then let's finish that homework one, and then midterm test everything tomorrow, and everything starting from the beginning and then finish everything. Okay, take care. Have a good day. Take care. Bye bye. Thank you. Yeah, you have a good night too. Thank you very much. Yeah. Yeah, we can finish this one tomorrow.